Hello everyone. So, in last few lectures we have learned the discretization of hyperbolic equations, parabolic equation and elliptic equations. So, we have learned some explicit and implicit schemes, and you know that the finite difference approximation of a certain order to discretize any derivative. So, now today we will discretize the stream function vorticity equation just to solve some fluid flow problem. So, we will consider steady incompressible flow, and we will consider momentum equations first, then we will convert it into stream function vorticity equations, then we will discretize that equation using finite difference method. So, you know what is vorticity, right, from fluid mechanics knowledge. So, vorticity is twice of the angular velocity or curl of velocity. So, in two dimensional situation you can write the vorticity will denote as omega. Okay. So, we are considering two dimensional. So, omega z. So, this is your del v by del x minus del u by del y. Okay. So, these omegas we are just representing as vorticity, and we are considering 2D steady Newtonian and incompressible flow. So, with these assumptions let us write the governing equations of fluid flow. So, that you know that one is continuity equation, then we have two momentum equations. So, we have continuity equation del u by del x plus del v by del y is equal to 0. So, this is your continuity equation. And you have momentum equations. Okay. So, momentum equations, now x momentum equations is steady we are writing. So, u del u by del x plus v del u by del y is equal to minus del p by del x plus, so this 1 by rho you can write minus 1 by rho, and this is your mu by rho. So, kinematic viscosity nu del 2 u by del x square plus del 2 u by del y square. So, x momentum equation. So, we considered u velocity, and y momentum equation you can write u del v by del x plus b del v by del y is equal to minus 1 by rho del p by del y plus nu del 2 v by del x square plus del 2 v by del y square. Okay. So, in this equation there are three equations, okay, and three variables u, v and p you have to solve. So, and fluid properties rho and dynamic viscosity mu are known, right. So, to eliminate the pressure from this term, because we want to solve a simplified equations which is convective diffusive equation first. Okay. So, we will eliminate pressure from these momentum equations. To eliminate pressure, so what you do, you just take that derivative with respect to y of this equation 1, okay, and you take the derivative with respect to x of this equation 2. So, what you do, you take the derivative with respect to y of equation 1, okay, equation 1, and subtract the second equation with respect to. So, you take the derivative with respect to x of equation 2. Okay. Then you, if you subtract, then you can see that the pressure term will get eliminated. So, you can see this will get del p by del x del y, okay, minus 1 by rho, and here you will get minus 1 by rho del p by del x del y. So, you can see that if you subtract, then this will be eliminated, and if you rearrange, then you will get the equations, vorticity equation. So, you will get u del omega by del x plus v del omega by del y is equal to nu del 2 omega by del x square plus del 2 omega by del y square. Okay. So, from these two momentum equations, okay, we could derive the vorticity equation just eliminating the pressure. Okay. So, you can see it is u is the x direction velocity, b is the y direction velocity, and omega is the vorticity, and nu is the kinematic viscosity. So, here nu is kinematic viscosity and omega is in this case vorticity. Okay. So, we could derive this vorticity equation, and which is convective diffusive equation, because in the left hand side convection term, and this is your convection term, and this is your diffusion terms. Okay, and this is your vorticity equation. Okay. But how to find u and v now, because vorticity equation you can solve for vorticity omega, but you need to know the values of u and v. Okay. So, for that we will use stream function. So, you know what is stream function. Okay. Stream function is a function which satisfies the continuity equation such that u is equal to del psi by del y and v is equal to minus del psi by del x. So, we define stream function okay. So, stream function is psi. So, it satisfied the continuity equation such that u is equal to del psi by del y and v is equal to minus del psi by del x. Okay. So, you see whether it satisfies continuity equation or not. So, you have del u by del x plus del v by del y is the plus del v by del y. If it is 0, then it satisfies the continuity equation. So, if it is, so del of del x del psi by del y and minus del of del y del psi by del x. So, obviously this is equal to 0. So, that means it satisfies the continuity equation. So, now we know the definition of vorticity. So, vorticity already we have defined, omega is equal to del v by del x minus del u by del y. Okay. So, now you substitute v here. So, del of del x, what is v? V is nothing but minus del psi by del x, okay, and minus del of del y, what is u? U is del psi by del y. Okay. So, you can see that it is minus del 2 psi by del x square plus del 2 psi by del y square. That means, you can write as del 2 psi by del x square plus del 2 psi by del y square is equal to minus omega. So, this is the equation for stream function. Okay. Equation for stream function. Okay. So, now this equation, this is obviously elliptic type equation, okay. So it is a Poisson equation. So for a known value of vorticity omega, you can solve this equation and can find the stream function psi. Once you know the psi, you can find the velocities, because u v you can represent as a gradient of psi. So from these expressions, u is equal to del psi by del y and v is equal to minus del psi by del x, you can find the velocities. Once you solve this equation, psi is known. So now if you go back and see the vorticity equation, now in vorticity equation, now u v you can get from the stream function. So that means you need to solve two equations. One is your stream function equation, okay, grad square psi is equal to minus omega, and the vorticity equation, which is your convective diffusive equation, okay. So that means now you have this set of equations. So you have u del omega by del x plus v del omega by del y is equal to nu del 2 omega by del x square plus del 2 omega by del y square, okay. So this is your vorticity equation and this is your stream function equation, and you can find u v from del psi by del y and v is equal to minus del psi by del x, okay. So obviously we have written the governing equations in dimensional form, and these equations if you solve, then you will be able to get the velocity distribution in a domain, okay. So we will discuss two problems and we will discuss about the boundary conditions, and we will show some results after solving these equations for a particular problems. So now we need to discretize this equation using finite difference method. So you have two different equations, one is stream function equation and one is vorticity equations. Now these two equations you just discretize using finite difference method, you know different scheme. So depending on your choice, you can use some scheme and discretize using finite difference method. So first let us discretize the stream function equation using finite difference method. So you have stream function equation del 2 psi by del x square plus del 2 psi by del y square is equal to minus omega, okay. So we will take a grid, two dimensional grid, okay. So you have I j, I plus 1 j, and this is your I minus 1 j, this is your I j plus 1 and this is your I j minus 1, and we will consider uniform grid, okay. So that means here the delta x is constant, this is your delta x, this is your delta x and this is your delta y and this is also delta y, okay. So delta x may not be equal to delta y, so we will define the beta is equal to delta x by delta y, okay. The ratio of the step size in x and y direction, delta x by delta y, we are denoting as beta. So this is second derivative of psi, right. So second derivative, so what we will use? We will use central difference approximation to discretize this second derivative, okay. So if you use second order method or central difference, so which is second order, so we can write psi I plus 1 j minus 2 psi I j plus psi I minus 1 j divided by delta x square. So this is second order accurate, you know, right, this approximation. Similarly in del 2 psi by del y square, so psi I j plus 1 minus 2 psi I j plus psi I j minus 1 divided by del y square, okay. is equal to minus omega ij. Okay. So, this is the discretized equation. Now, you just write psi I plus 1 j minus twice psi I j plus psi I minus 1 j, and we have defined beta is equal to delta x by delta y. So, we can write beta square psi I j plus 1 minus twice psi I j plus psi I j minus 1 is equal to minus omega I j delta x square, because delta x square I have multiplied, okay, both side. So, delta x square by delta y square I have denoted as beta square, and delta x square is coming here minus omega I j into delta x square. Okay. So, after simplification you can write it as psi I j minus 1 plus psi I minus 1 j, okay, minus 2 into 1 plus beta square psi I j plus psi I plus 1 j beta square psi, sorry, this is your beta square and psi I plus 1 j and plus beta square psi I j plus 1 is equal to minus omega I j delta x square. Okay. So, this is the discretized equation. So, now you have to choose whether you will use implicit method or explicit method to solve it. Okay. So, you can see that psi I j you need to find. Okay. So, if you explicit type method if you use, then you can write psi I j which is your unknown. So, psi I j is equal to, you can write psi I plus 1 j plus psi I minus 1 j plus beta square. Okay. So, this I am taking this side, so beta square psi I j plus 1 plus psi I j minus 1, okay, and this minus, so it will become plus. So, it will be delta x square into omega I j divided by 2 into 1 plus beta square. Okay. So, if you are using some solver which is explicit type solver, then you can solve for psi I j at time at iteration level k plus 1, and all you can take at best available value. So, here you can see that although you are solving for psi, but you have to know the value of omega, okay, and this omega you have to get it from the vorticity equation, and you can see that this way these two equations are coupled, because when you are solving the stream function equation you need to know the value of vorticity omega. Similarly, when you are solving for vorticity equation you need to know the velocities u v, which in turn actually you need to know the stream function. So, these are coupled equations. So, you have to solve simultaneously. So, now we have discretized this equation, stream function equation, and psi I j you can solve using this expression, okay, for the known value of omega I j. Now, let us discretize the vorticity equation. So, now we will discretize vorticity equation. So, what is the vorticity equation? U del omega by del x plus v del omega by del y is equal to nu del 2 omega by del x square plus del 2 omega by del y square. So, u is del psi by del y. Okay. So, you can discretize this, okay, in 2 dimensional grid. If you use, this is your I plus 1 j, this is your I minus 1 j, this I j plus 1, and this is I j minus 1. Okay. So, now if you want to find the value u, at point ij, then you can discretize using uij, okay. Uij del psi by del y, it is the first derivative. So, you can use some second order approximation. So, that you can use central difference. So, you can write uij. So, it is a first derivative del psi by del y. So, you can use some second order approximation. So, we will use central difference. So, you can write psi I j plus 1 minus psi I j minus 1, and the distance between these 2 points is 2 delta y. Okay. So, this is your uij. Similarly, v is equal to minus del psi by del x, right. So, vij, and if you use the central difference approximation, then you can write psi I plus 1 j minus psi I minus 1 j divided by 2 delta x, okay, because we have used central difference approximation for this first derivative, and the distance between the 2 points is 2 delta x. So, psi I plus 1 j minus psi I minus j by 2 delta x, and psi you already you can find it. So, psi you can find it from the stream function equation, already we have discretized that equation. Okay. So, from the known values of psi you can find the values of u and v. Now, you discretize this equation. Okay. So, here also let us use the central difference for the first derivative and central difference for the second derivative. So, that overall order of accuracy will be delta x square and delta y square, because the stream function equation already we have discretized using second order approximation. So, the order of accuracy is delta x square and delta y square, and when we are going to discretize this vorticity equation, let us take central difference approximation. So, the order of accuracy will be delta x square delta y square. So, we will take the central difference approximation for both first derivative and second derivative. So, you can write u I j del omega by del x. So, omega I plus 1 j minus omega I minus 1 j. So, central difference divided by 2 delta x, okay, plus v I j, then omega, now del omega by del y. So, this is I j plus 1 minus omega I j minus 1 divided by 2 delta y. Okay. Now, in the right hand side we have the second derivative. So, you will use central difference. So, you will use omega I plus 1 j minus twice omega I j plus omega I minus 1 j divided by delta x square. So, this is the first term, and the second term you can write omega I j plus 1 minus twice omega I j plus omega I j minus 1 divided by delta y square. Okay. So, you can see overall the approximation is second order delta x square delta y square. So, now you rearrange it and you define beta is equal to delta x by delta y. Okay. So, if you rearrange it you are going to get, so you can see what are the terms are there. Okay. So, omega I plus 1 j here, omega I plus 1 j here, okay. This will take common, then omega I minus 1 j here, omega I minus 1 j here, okay. Then we have omega I j plus 1 here, omega I j plus 1, and now we have omega I j minus 1 and we have omega I j minus 1, okay, and we have omega I j here and omega I j here. Okay. So, now you rearrange it and write. Okay. So, multiply both side by delta x square. Okay. So, that we can write in terms of beta. Okay. So, delta x square. So, you can see this omega I plus 1 j. Okay. So, omega I plus 1 j. So, if you write omega I plus 1 j, so it will be okay, multiply both side by delta x square and divide both side by nu. Okay. So, that here nu will come in the denominator. So, now we can write. So, what is the coefficient of omega I plus 1 j? So, omega I plus 1 j. So, it will be minus 1 minus u I j. Okay. So, we have multiplied by delta x square. So, it will be delta x divided by 2 into nu. Okay. It will be omega I plus 1 j. Similarly, omega I minus 1 j. So, I minus 1 j. So, it will be negative. So, you can, it will be omega 1 plus u I j delta x by twice nu omega I minus 1 j. Okay. Similarly, now you write omega I j plus 1. So, omega I j plus 1, if you write, then it will be minus. Okay. So, it will be beta square. So, it will be beta square. So, it will be 1 minus. So, v I j. So, we have multiplied with delta x square. So, it will be delta x square. So, delta x by delta y will be beta. Okay. So, it will be delta x square. So, beta square, and this is delta y if you get it. So, it will be v I j. So, delta y divided by 2 into nu and beta square will be there. So, it will be beta square omega I j plus 1. Okay. Because here delta y is there. So, if you multiply both side delta y, so denominator and numerator. So, it will be delta y by delta y square, and delta x square you have a. So, delta x square by delta y square will be beta square, and that we are taking common. Okay. Similarly, you write for omega I j minus 1. So, it will be minus 1 plus v I j delta y by twice nu. Okay. Then beta square omega I j minus 1. Okay. And now you have in right hand side. So, you have omega I j. So, nu we have already divided. So, it will be omega I j. So, it will be minus 2 into 1 plus beta square into omega I j. Okay. So, now you can write for omega I j. So, omega I j is equal to, so minus in both side it is there. So, 2 into 1 plus beta square. Okay. And so, it will be, so it will be 1 minus u I j delta x divided by twice nu omega I plus 1 j plus 1 plus u I j delta x by twice nu omega I minus 1 j plus 1 plus b I j delta y by twice nu beta square omega I j plus 1, and you have plus 1 plus v I j delta y by twice nu and multiplied by beta square omega I j minus 1. Okay. So, now you can substitute the values of u I j and v I j, because u I j v I j you have written in terms of psi. So, if you substitute it, then you are going to get omega ij we have written, but now we can substitute uij and vij. So, uij is psi ij plus 1 minus psi ij minus 1 divided by twice delta y, and vij as minus psi I plus 1 j minus psi I minus 1 j divided by 2 delta x. So, now we will substitute this ub in the expression of omega ij. So, omega ij is 1 by 2 into 1 plus beta square 1 minus, now we put the value of u. Okay. So, it will be psi I j plus 1 minus psi I j minus 1 divided by 2 delta y delta x by twice nu. Okay. So, this is omega I plus 1 j, then plus now 1. So, minus, so it will be plus. So, psi I j plus 1 minus psi I j minus 1 divided by 2 delta y delta x by 2 nu omega I minus 1 j. Okay. Then next term now 1. So, it was minus, but velocity Vij is having negative sign. So, this minus minus will become plus. Okay. So, psi I plus 1 j minus psi I minus 1 j divided by 2 delta x delta y by twice nu. Okay. Then beta square omega I j plus 1 and 1 minus. So, here plus was there, but now Vij you have negative. So, this negative here it will appear negative. So, psi I plus 1 j minus psi I minus 1 j divided by 2 delta x delta y by twice nu beta square omega I j minus 1. Okay. So, now you substitute beta is equal to delta x by delta y. Okay. Here delta x by delta y and here delta y by delta x. So, you can put beta. So, if you write omega I j, so you will get 1 by 2 into 1 plus beta square 1 minus psi I j plus 1 minus psi I j minus 1 beta by 4 nu. Okay. Delta x by delta y are putting beta omega I plus 1 j plus 1 plus psi I j plus 1 minus psi I j minus 1. Okay. Beta by 4 nu omega I minus 1 j plus 1 plus psi I plus 1 j minus psi I minus 1 j by 1 by 4 nu beta. So, beta delta y by delta x is equal to 1 by beta omega I j plus 1 plus 1 minus psi I plus 1 j minus psi I minus 1 j 1 by 4 nu beta beta square omega I j minus 1. Okay. So, this is the discretized equation for omega I j in dimensional form, and whatever psi we already derived, psi I j is 1 by 2 into 1 plus beta square. Okay. Psi I plus 1 j plus psi I minus 1 j plus beta square psi I j plus 1 plus psi I j minus 1 plus delta x square omega I j. Okay. So, this is the discretized equation for psi. So, you can see in the psi discretized equation omega I j is coming, and in omega psi values are coming. So, it is coupled, and you need to solve this psi I j and omega I j for all interior points. So, whatever these equations we have derived for the stream function and the vorticity. So, these are applicable for the interior points, but we need to solve some fluid flow problem. So, in the next class we define some fluid flow problem, and for those problem we will define the boundary conditions and we will discuss the boundary conditions for omega and psi, because when you are solving these equations, this vorticity equation and stream function equation, you need the boundary values as well in terms of psi when you are solving for stream function, and you need the values of vorticity at the boundary when you are solving the vorticity equation. Okay. But you may know the boundary condition in terms of velocities, okay, for a particular fluid flow problem. So, from this velocity boundary condition you need to derive the stream function boundary condition as well as the vorticity boundary condition. Then only these two equations whatever we have derived today for the interior points, you will be able to solve for a particular problem, provided the boundary conditions are given in terms of stream function and vorticity. So, in next class we will discuss two problems and we will describe the discuss the boundary conditions for those two problems. Thank you.